Hello, Saturday, January 6, 2024. I wanted to get started on problem 14 before lunch. First, my voice is a little rusty, sorry about that, but it's very, very cold in Denmark this year, more than usual, but that's to be expected when we are in an El Nino year, as we are. A quick note to problem 13. At the end, I used a trivial observation, but I didn't state it. If we have F1 lying in MK1 with the character Chi1 and the same for F2, then their product lies in the sum of the k's and the multiple of the two, or the product of the two characters. And if we say put this to mth and this to nth, then they just come on here. And I, of course, used it with n being equal to -1. So this is chi2, the inverse. So that's chi2 conjugated, but it was a real character. So that's why, but it's all very trivial, and I just thought it and didn't think about writing the general principle. Now, going to problem 14. We need to find out the group, the Hecke group df2 over gamma 2. I forgot about this group. And next we need to find out what this means. And I think it believes that theta to the fourth lies in this group, and when we have not that was not right, but in, you know what I mean, in m of theta 4, and that's m2, and then if we have a gamma in this group, then we have a character on G2, which is constant on gamma of 2. So we need to find out what is this character and then go about proving it. So I found my notes on the Hecke group, and it's generated by S and T squared. So that's a fundamental domain. And it has two cusps at 1 and infinity. I've drawn it like -1, but we can just move this 2 to the right, then we get the cusp at 1. If you map it modular 2, then it's either then it gives the unit matrix or S modulo 2. So that means we can use the character defined on D. Very simple. So if D is 1, it's the unit matrix, it should give +1, so it's a minus here. And if D is a multiple of 2, then it gives -1. So that's our character. Then I wrote up the transformation formula for theta. So we need to make the one for, I wrote the transformation formula for capital theta. So we need the transformation formula for minuscule theta. So we substitute z halves. That looks like number 2. And this is just minuscule theta of minus 1 divided by z. So that's lovely. And that means that minuscule phi of z, oh, we don't need that, minuscule phi operating on S is I to minus 1/2. Let's just write that. No, the square root of I, yeah. The square root of I times phi, is set to minus 1/2. Oh my god. You know what, I'll just write what it says. It's 1/2 here. So it's set to minus 1/2. So let's put a z on it here. And then when we isolate this, we get to plus 1/2. So we end up with the imaginary unit to minus raised to minus 1/2 of phi of z. Meaning, of course, that raising to 4th order and obviously we also have that phi g to any k to t squared, of course, because we need to add 2 to get an integer of an integral multiple of 2pi equals phi. Translates correctly under gamma 2 and gamma 2, it has the cusp of, as far as I remember, it was a cusp of at infinity, naught, and 2 and 1. It's weird that this has fewer cusps than gamma 2. We'll just check. Yeah, I was right. Infinity, naught, and 1. Here it's obvious. 1 plus 2 q2 square root q, and then 4, that gives 2q squared, etc. 9. Oh, what does this give? It's 9 halves. Yeah, of course. So it's Q2. Yeah. So that's all right. It has the right form. And phi at infinity equals unity. At naught, actually, this is silly. It's phi to the fourth I needed to find out, but that's the same, of course. It's the same. So it's the same value. And then at unity, so we need a matrix for unity. Mapping infinity to unity. Oops, that's not very nice. Oh yeah, it's any in gamma. It must not lie in gamma 2, can't, but it can lie in gamma. I would actually like to write it. I wonder if it could be written like STS. Well, that's fine. Oh, we're just taking -1 instead. Oh, we could just put t to minus first up here, I think. There we go. Let's do to the fourth, yeah. We already know it's invariant under S. So we operate with t minus first. So what does that do? We'll just write it over here. Minuscule theta of z plus 1 equals this means that the odd n change sign and the even n are retained. Actually, we did prove this with the capital phi in another problem. So I think we can just use that and then substitute. Oh, actually we did. We don't need to do this. This is capital phi of z halves plus 1/2. And that's problem 8a. It equals 2 times theta of 4 times z, that's 2z, minus theta of z halves. And that's 2 theta of 4z minus minuscule phi of z. And now this is the wrong notation, because it's we're operating on this function as a whole, not only on 5z and then replacing z with 4z afterwards. I feel confident I've made a mistake here. Actually, it's a good place to make a break here. Then I can find the mistake before going on to show that it transforms correctly when we have a gamma in the Hecke group. I have had my lunch, made a cup of coffee, and after lunch I looked a little at what I've done. It worried me that I got z divided by 4, because this is a group of level 2. So getting the 4th root of q, that was quite a surprise, because based on, I don't know if it was problem 1 or problem 2, this should have period 2 then. We just had to check that there were not too many negative, but let's look at it and see what we get. Now here I have several things to say. First, making these notations, I really don't like them anymore, so we should do something else. So first, it's 1/2. You see, going down here, when we take this difference to 4th power, then we have a problem. So we reduce it first as is. And then I really hate this notation, so I have figured out a way to work with it. I don't know if you like it, but let's see. So it's phi, and then to order 1/2. 1/2. And then instead of this, we just say, well, t to minus first, that's a function as well, which just translate it to the left. So it's just like that. And then 4 times z, these z's must be taken away. And we just compose it with the function 4, which is to be understood that it's a multiplication. And then, of course, later on we will apply s to this, and we'll see. So it gives 2 to, where do we have it up here? I to minus 1/2. and then it's psi, and then 4 sz. And then just phi, not phi var, but phi, never mind. And then we need this guy. And there we actually have to put 4 into here. That is, we have to there's a little problem with the algebra here, because we do get, of course, set forth, and the constant has vanished because it's to 1/2. Of order 1/2, so it's the square root of 4 that will cancel this 2. Actually, I'm not quite sure how to do that. I think we'll actually have to do that by using the transformation formula. But let's just leave it for the time being. So we end up with this. And let's delete this so I can continue. So this, of course, is 1 plus 2k4 plus 2k4 to 4th plus 2k4 to 9th minus 1 plus q4 to 4th, 2 of them, plus 2, that's k to 9th, that's k4 to 36, etc. And you see units are gone away, so we get 2 q4th, these two cancel, and then plus 2 q4 to 9th plus, and you guessed it, 4 to 16th. Nope, it's only the odd ones we get here. It's 25. So I don't hope you guessed it. You see that this function is actually periodic with a period of 2, but q2 does not occur. But when we take it to the 4th, then it's 2 to 4th. And then we can take q4 Q4 out, so it's Q, and then 1 plus Q4 to 8 plus Q4 to 6, the triangular numbers, all to 4th power. So you see the value at unity is 1, and this guy actually is periodic with the period 2, as we proved in problem 1 or 2, I forget which it is. This proves that this is that phi to 4th actually lies in gamma 2. So the only problem, now I forget the generator of the group here. Why didn't I write? Oh, it's here. It's s and t squared. We know it's invariant under t squared, so it's just s that is the problem, but we already have that. Oh, that's weird. This is wrong. It's actually a minus, because this to the 4th gave I squared. So there's a minus here. And that's exactly the point. That finishes the proof. At the end of the video, I just wanted to present the formula I derived. So we take the transform with respect to this kind of matrices. It might be unity, so it's S, but we also had it with n equals 4. And I've even introduced it with n equals 2. So we have the transformation, and then we look how does f of r set work. And this seems to be the general formula. Here r is the number. So if you really wanted to distinguish between numbers and functions, then you might write r of unity to minus kth. But I don't think that should be necessary. And then times g composed with r, with the reciprocal of r or the inverse of r, however you like to see it. So it's a straightforward computation. We've done it many times, really, but I just wanted to show the general result, that we don't have to do the particulars another time.